Hey, it's Phil from statisticsmentor.com. What we're doing here is we're introducing the derivative. So what is a derivative? The idea of a derivative is that it gives us the slope of the function at a certain point. Example, consider this function x squared, which I'm denoting by f. Some of you in your schools, you'll denote that by y equals x squared, but it doesn't matter, it's just a symbol. So we know that it looks like this U-shaped curve. What we can see here is that the slope at various points x, the slope of the function changes. Example, when we're looking at, so this is 0, these are positive values of x, these are negative values of x. If we consider the small values of x, you can see that the slope here is shallower than the slope for higher value of x. You can see that as x is increasing, the slope gets steeper and steeper. Moreover, the slope when x is positive, the slope is positive. The slope is upward sloping. Whereas when x is negative, the slope is negative. Okay, now we said that for initial values of x, the x is shallower than for higher values of x. The exact slope is given to you by calculating the derivative at a certain point x. So we'd expect the derivative of the x here, the slope here, to be small and positive, whilst the derivative of the higher value x here to be positive and bigger than the value for here. We would expect the slope here to be negative and small in relationship to a point here, say, where we'd expect the slope here to be negative and bigger value than this one. Finally, when we get to the point here where it actually slope changes from negative to positive, it goes flat at some point there, so we expect that a certain point of x that the slope is 0. So that brings us on to the next question. What's the point of calculating the derivative anyway? What does it tell us? Well, we can use it to answer questions such as rate of change, which I've just kind of shown you on the graph here, because the size of the derivative at a particular point x will tell you the rate of change of the function at the particular point. And the bigger the value, that means the faster the rate of change at that point. That means the function is changes a lot when x moves up by a little. So we can use it to answer questions about rate of change. We can also use it to help us sketch graphs, because we can use derivatives to help find turning points, what are known as turning points. Turning points is where the gradient changes from negative to positive or positive to negative. So here we can see if we're going this way it's negative, this way it's positive. So derivative can help isolate the point where the gradient is actually 0, where there is 0 change, i.e. the gradient is neither decreasing nor increasing. We can see in the picture it's about here, in fact it's at x is 0. Right, and once we've found turning points, it helps us to kind of sketch. We know where these, as the name suggests, the turning points are, where the curves are, from positive to negative or negative to positive. Next, we want to address the issue of notation. Now, if I denote my function by fx, the derivative of the function with respect to the input, what they call the variable, is denoted either by straight d, notice df by dx. This is read as the derivative of the function f with respect to x, and that basically means that what happens, how does the function change if x changes by little. That's the notion of rate of change. Another notation for this you'll see is some f dash f dash x, or you might see it as f subscript x. In terms of jargon, if you're asked to do differentiation, you could be phrased in terms of as follows: differentiate the function f with respect to x, or you could be phrased as find the derivative of f with respect to x. Okay, that's notation and terminology. Next, derivatives. What we have, the example I've given you here is a function that has just one variable, one input. But we can find derivatives for functions like this, where there is only one input. But we can also talk about derivatives of functions that have more than one input. So for example, here I've got a function that has two inputs, and so on. I can have three inputs, and on and on and on, like that. Now in the case where we are talking about derivatives with more than one input, here we've got two inputs, here we've got three inputs, we don't talk about derivatives, we talk about partial derivatives. Partial derivatives. And the idea of partial derivatives is what happens to the rate of change of the function when one input changes by a little bit but holding everything else constant. That's why you get the word partial, because only one bit of it changes, all the other inputs stay the same. Okay, so now we know what a derivative is, we have an idea of what it's useful for. We've looked at the notations, and we've talked about derivatives versus partial derivatives. Because this is an introduction, I don't want to focus too much on partial derivatives, because partial derivatives are not for introductions. Just note there are different notation for partial derivatives. If some of you looked in your textbooks, you'll see they use curly d instead of straight d. So you know that they're talking about partial derivatives when they start using curly d's like this. Alright? I just talk about this because in economics you kind of use the partial derivatives a fair bit. Okay, now we present the very basic rules of differentiation. First, the derivative of a constant, a number, is always 0. So let's say a be a number, any old number, then dA by dx is equal to 0. Why? Intuitively, it's because if x changes, a constant, as it suggests, never changes, so irrespective of what x changes by, a is never going to change. 0. Next, probably the most important one in this tutorial is, say I've got a function fx, and it is equal to, say, x to the power of a number, a. Then the rule is that if I want to find the derivative of this thing, let's make it big because it's important, I bring this power down and I subtract 1 off that power. Okay? And I should say that this is for any value a and the real line. Let's look at some examples. Let's say fx is equal to x to the power of 8, then derivative of f with respect to x, take the power down, this power subtract 1, 8 minus 1, 7, done. Next, f, now since I said it can be for any number on the real line, x to the power, I can have negatives, 5. What's going to happen here? Same thing. Take this down, so now it's minus 5 x minus 5 minus 1 minus 6. Okay, notice not minus 4. Minus 5 minus 1 is minus 6. Next, f. Now if you get the hang of this, once I've given you the question, you just pause the video and have a go. Derivative of x. Well, I want to derivative of x. Now nothing's written there. That's the same as saying something to the power of 1. 1 comes down. 1 times x is x. 1 minus 1 is 0. A number to the power of 0, finite number to the power of 0 is always 1. And one more. fx equals x to the power of a half. Aha. But I did say that this power can be any number on the real line, so we can take fractions. Comes down, the power minus 1, so a half minus 1. Now those of you, if you can't use a calculator, notice that trick here is, instead of saying minus 1, pick the denominator, make a fraction where the denominator is the same as that one. Okay, minus 2 over 2 is the same as 1. And here, let's do it aside here. And once we've got this where it's common denominator, you know that it's just numerator can be subtracted from each other, divided by the common denominator, and that gives us minus a half. Right, so that's another rule. So I've now introduced the basic rules. The next thing I want to ask is, and I should have asked this earlier, is does the derivative exist for all values of x?